Okay, it looks like Molly's got us going. So as I said, this is the OSU Land Steward Program. This is our community education series. We love ideas from the community about speakers or topics. We have a group of volunteers that puts these things together and contacts our instructors. So if you have ideas, drop those into the chat. We have Molly Nix with us today as she's from the education committee and she's a co-host. And if things really go sideways, she might become your host. So if suddenly someone else is in charge, you'll know what happened there. But we like to have redundancy. To hear about upcoming classes, you can visit our website, which there's that long website. I'll drop that into the chat after a bit, or you can just Google the OSU Land Steward Program. And again, I'll put it into the chat. And I'm going to show you what's coming up. You'll find, if you go there, you'll find our upcoming events. So this is us for this evening. We have the carbon sequestration through trench composting. September 7th, we have a walkabout in Phoenix called Follow the Water, Protecting Water Resources, which is really one of my favorite topics. It's something I used to teach. It's walking around, kind of seeing how the urban landscape interacts with water and our streams. And that'll be with Francis O. Young from the Rogue River Keepers. And that's going to be kind of a smaller group and is a nice way to walk around and see some cool things that are happening in our local towns. We have in September, our land steward training is going to be in the field this year, which I'm really excited about. It is full, but you could get on the waiting list. Occasionally, really pretty frequently, 1 or 2 people have other life things that come up and they have to drop out. So you could get on the waiting list. We're very excited. It's a great program, goes September through November and really through the spring. You learn all about kind of managing natural resources on your property. We're excited about that one. And then September 14th, we have this will be a Zoom program, attracting native birds to your garden. So again, you can go to our website and find out more about all of those. So with that, I'm going to introduce Scott Goode, who is an environmental scientist who has worked on water treatment, bioremediation, research in the role of environmental factors in soil chemistry. He lives in the Rogue Valley and is currently a research scientist with the University of Nevada's Desert Research Institute in Reno, Nevada. And he is also a land steward. So I'm going to switch over to his presentation here and give him control of my computer. Let's see, did we have that one up? I'm not sure. Okay.
It's right down there in the toolbar.
Here, you think? There it is. Yeah. Okay. Except it doesn't really look like that's what I'm seeing. Molly, can you confirm that you are seeing the right
I'm seeing
Scott's presentation?
Can you hear me? Can't hear me.
Shoot. Anna, you could go in the other room.
Yeah.
Can you hear me?
And there might be chats. Here we go. Let me check the chat. Okay. So Molly is.
The presentation's on screen in the other room.
Okay, great. Then I'm going to just let Scott take my seat and go over and drive from the other room.
Okay, doke. Let me see. There we go.
I've never.
Okay, though. Pardon me.
You can make this smaller if you want.
Oh, yeah. That's it.
With that corner, I had it just dragged over this little corner right here.
Oh, I see. Over here.
Yeah, here I'll.
Oh,
there we go.
okay.
That's probably all you need. And you don't need. Oops, hang on. You don't need that one.
All right.
Okay.
Oh, great. Okay, this is wonderful. Okay, pardon me.
Gonna go in the other room.
Yeah, the skill that I've just observed in putting together this presentation is really remarkable. Rachel is absolutely amazing to be able to put this together. This is basically a presentation about kind of the interlacing of the land steward experience and citizen science, and a direct material engagement with climate, or doing something practical about climate change, actually making a change in the climate by what you do on the landscape. And what I'll be presenting is basically just my observations from field geology and soil science and composting and gardening, and learning from some traditional agricultural systems that predate European European culture on this continent. And so these components sort of drive an interest that the land steward program is really, really good at helping you work through. So let's see. Click here. I'm not advancing. Click here. Click here. Yeah.
Hold on, that's Rachel.
Yeah, it's not advancing. I've been trying here for a bit.
Just like, I think get maybe onto that one. There we go.
Okay, good.
Okay, thank you.
All right,
Yep.
great. Okay, doke. So I have taken these experiences and
What do you want to do?
I want to get this closed caption.
Just leave it.
No, I have dyslexia. I can't do this. If this is here, I won't. So how do I?
One more. Okay, now?
Well, see, it spells out everything I say, and
Yeah, that's live transcript. Is that distracting?
yeah, terrifying actually.
Okay. Let's turn off live transcript.
Okay. Yeah, I was looking for that. I can't. More.
Okay, we're getting going here, folks.
Okay. So, pardon me. I took all of the things I described there, and I found myself in an opportunity where I was sort of between jobs and kind of deciding how to engage my skills in doing, research, and that could eventually turn into, something interesting. And I've always been interested in waste stream conversion, efficient waste stream conversion, and having an interest in that, and then being in field geology classes where I'm seeing these seams of very, very young lignitic coal that are so similar to what I'm seeing, in my compost, that I just wonder what the transformation. They're clearly different chemically and everything. One is generating humus, and the other one is generating or is made out of a form of carbon of about the same amount of carbon, and yet it stays in the ground for millions and millions of years. You can plow it and it won't go into the atmosphere, and as long as you don't set it on fire, the carbon that's in it will stay as part of the soil. So this is kind of, what people would be looking for if they were actually looking to see how or the form that nature holds all of this all of this carbon. So looking for that link between composting and the geology has always been a real fascination for me. Click here. There. Yeah. Okay. Pardon me. So after working on this technology in Boulder, an acquaintance of mine, actually a family friend, came out and saw what I was doing there, and when he decided to retire, he said, I'd really like to see this happen. So let's find a piece of land and, see where this research goes. And so we put together this concept to one of Eric's nieces, and she took the idea of the transformation of biomass into this carbon form, and came up with this as the emblem of that. And so you have the carbon that's inside of biomass, and it is forming into this mineral form, and is moving downward. And I just was amazed when she came up with this, because it's so beautifully addressed what we were working on. So we acquired a piece of land. It was an interesting challenge because the real estate agent would call in with a location. I would sit down with the soils maps and the topographic maps and hydrological maps and all of these things, and more often than not say, no, I don't think we even need to look at that. And he would just say, you haven't even seen it. You have no idea what it looks like. What, I said, no, I have a pretty good idea what it looks like from altitude, but, but eventually came across this piece of land. It's a piece of terraced, upland terrace above a floodplain, beautiful upland terrace soils, and with exactly the perfect aspect for spring through fall and fall through winter to spring soil orientation. And so we acquired it, and shortly thereafter started trying to put together some kind of organization that could, actually accomplish all the things that that emblem suggested. So when in 2011, shortly after buying the land, I took the land steward course, and you can see here that from very early on, carbon sequestration cells, the ones we'll talk about this evening, garden trenches. Well, it turns out that once you have the garden trenches there, you don't need a worm bin, because the worm bin is in your garden. So you don't even have to move the worm castings. They're there. So you can sort of cross it off the list. And so from that trench in Boulder, I sort of took what I had learned from that and began the kind of next iteration of the things that I learned there. And the first thing that I had really changed things was to understand that the soil is actually composed of these layers, and that each one of those layers in a healthy soil is interconnected with the next. And as long as the biomass of the above ground detritus or above ground growth turns into detritus that goes efficiently through the detritosphere, then the nutrients that are in the crop that just grew will be returned to that soil in a remarkably short period of time. And the drillosphere and porosphere are the systems that make that happen and deliver nutrients very, very rapidly to the rhizosphere where the plants are growing. So, you can sort of separate each one of these out. Now, I have some sort of issues with the way this is sort of displayed, but we'll look at each one of these individually. But you can see that their definition of a rhizosphere is what is often called the rhizoplane, which is the zone immediately around the root, where root hairs can actually engage. And that zone is transcended by mycorrhizal fungi. And it has the entire rest of the soil column to look to. But the rhizosphere in many cases is talking about just that zone immediately around the root. And the reason it's confined to that is so complex that to take it any farther than that wouldn't give justice to what's going on right there at that surface. So the way, if you look at the biology of these systems, that you have the rhizosphere and there's a chaos, a riot of all this biology because the plant is exuding exudates and hormones, and the biology around it is exuding exudates and hormones, and they're transferring those. And so there's a lot of activity. And the fact that they put the detritosphere right next to that is really, really wrong. The detritosphere actually has to be as far away from that as possible, because what's happening in the rhizosphere is simple stuff is becoming complex stuff. And in the detritosphere, complex stuff is becoming simple stuff. And the chemistry of these two things are exactly opposite. And try to do them in the same place is really, really difficult to do. And as a matter of fact, what happens when you try to do that is that you give off a tremendous amount of carbon dioxide that otherwise would have turned into recalcitrant carbon in the soil. And the zone that connects those two is the porosphere. The porosphere is actually composed of two components. One of them is the pore between the grains, and the other is the surface of the grains. And they are very, very different, very distinct ecological environments and do very different things. So the detritosphere is where, as efficiently as it possibly can, all of these different kinds of life forms are transforming, first of all, the sugars, and then the carbohydrates, and then the fats, and all the way down until they get to things like lignin and cutin and all the very tough bits that are left over. I don't know if you've ever tried to compost, like say, Brussels sprout stalks. It will not happen. It just won't happen. And the reason is because they're made out of materials that just absolutely will stand up to that. And so there's a broad spectrum of different kinds of biomass in its response to this. And under the right conditions, even that very, very tough material can be transformed. But that's what the detritosphere does. It cycles nutrients out of above ground biomass and down at least underground. And right beneath the detritosphere is the drillosphere. And drillo is the Greek for things that crawl in, on, and under the ground. And what this is the zone that takes all of the organic material that's raining down from above to the detritosphere and mixes it with minerals that come from sometimes very, very deep in the soil. And it mixes those two together, the mineral phase and the organic phase. And for instance, as it takes both of those into its gut and it pulses that peristaltically through its system, it squirts organic material into the interlacings of clay particles, and it becomes one of the most recalcitrant zones in soil organic matter. There's a whole designation for that sort of process. And up until people started looking at the drillosphere, they couldn't figure out how the organic matter got in there, because there wasn't any soil physics that could have put it there. And it was because it has to go through a gut of one of a whole number of geophageous organisms. And there are lots of them, and they all live in the drillosphere. And so what they do is it's a little hard to see, but this thing that looks like a banana up here is supposed to be a piece of detritus coming in. And this is the mouth of the worm, and it spins around. And of course, this is where the fecal pellet is coming out. And it comes out, and if you actually look in detail at each one of these, I won't go into them, but they'll be available in the PDF that you can get for this. But there are remarkable things, like for instance, all of these potworms begin to eat up and degrade one of these fecal pellets. And as it does, mycorrhizal fungi come in, and this is where they dispose of kind of the fluid that drives their entire plumbing system. and it's a protein called glomalin, and it sort of leaks out the end of the pipe. Well, what it does is it fills this fecal pellet full of this and very, very sticky, very, very resilient organic matter. And so when you end up with a worm casting, it is actually much more complicated than just poo. There's all the stuff that happens in it. And some of the most important, well, if you look at where the actual soil organic matter is, when you talk about sequestering carbon in soils, it's all in living things or their poo. That's pretty much it. And if they die, not only are they not there, but the material that you are counting on as recalcitrant carbon is gone as well. And so that's how important the drill is for, really is in a functioning soil. And there's all of this beautiful and integrated transfer of nutrients and so forth. And through this mucus, this is really the same thing as on the inside of the intestine, because in this mucus, there is a microbiome, just exactly like is in the inside of the gut. And it's leaving behind its detritus or its extracellular polymeric substances all over these the walls of these, and storing all sorts of nutrients and biology in them. So adjacent to all of that activity is where you get away from all that activity and you start getting into where the soil part of the soil is. And it's really composed of two components. It's the spaces in between the grains and the spaces on the grains. I didn't have time to include it here, but I have some photomicrographs of fungi drilling into sand grains, quartz grains, others into feldspar grains to extract these organic acids, to drill down in there and extract out of the mineral lattice the zones that have these nutrients in them. And that's what's happening in the other part of the porosphere. The interesting thing about it is that water moves through this with irrigation and the time of the year and so forth. And so you have these little tidal pools in here, and then above it you have this little cavern. And so there's this constant change in the chemistry that's going on between open spaces and closed spaces. So the result of all this is that you end up with, in addition to this porosphere, there's this aggregatosphere that is the surfaces of those grains. And the joining of those two, the pore space and the actual aggregates, is what is at the basis of good soil structure. And the beautiful thing about it is it's all made out of organic stuff, which doesn't dissolve in water, or it becomes less soluble with time. And if you look at the rhizosphere, it co-evolved with, the earliest plants. The reason that these plants could grow up is because fungi mainly went out and built a network of fungal hyphae that supported the growth of these trees. And the taller they got, the more chlorophyll that they could develop and the more sugar that they could generate, which is what the fungi were always interested. And the plant's roots just transfer that back in, from the sky into the soil. And so the biology that sets up around that in the rhizosphere is this really complex, like hormones that the plant needs in order to do some of its metabolic processes are made out in the soil. They're transmitted by, into the roots and up to the plant in order for it to sustain that kind of growth. And so as the plants grow through time, you have a soil without a plant in it, and you have this kind of casual stroll of biology through here with a few remnants laying around on their way to decay. But as soon as a plant starts growing, a structure begins, a fractal into the soil. It's a living fractal. And as it grows out, depending on where the nutrients are, where the moisture is, where the sunlight is, where there's ground cover, where there's not. It builds this incredible network that sustains the plant above. And in the process, it extracts all the nutrients out of the soil and puts it up into the plant. And to the degree that all those nutrients make it back into the soil, that demonstrates the biological efficiency of a site. And that's kind of what regenerative agriculture is, that has as its underpinnings. So here's a system that we use where you grow a crop and you make sure that all the biomass from the crop goes directly in the trench. And because the decomposition, the detritus sphere down here is so efficient that these trenches sink all the time. As a matter of fact, we have to really work hard to keep enough biomass coming into these by harvesting not only the plants that grow there, but all the weeds all the way around the yard and cover crops that we grow in other places and there, just to keep this system going. So it's voracious. And what's happening is, because they're using facultative anaerobes, this is the same thing that botany utilizes, this zone of biochemistry. And the interesting thing about it is that these guys can go back and forth between aerobic and anaerobic. And so what they do is they keep this equilibrium going in the soil in a way that very, very efficiently transforms organic material into its nutrients and fragments all of the carbon that's in it and leaves it behind as a detritus, which goes down into the bottom of the trench. And as long as that never touches soil, it'll accumulate. So you have to put this hugelkultur zone at the bottom of it to make sure that this never touches soil, because if it does, it'll go away. And so here you have detritosphere, drillosphere, porosphere, rhizosphere, upper plant, back of the ground. And so all you're doing is cranking the same nutrients through. And it's so efficient that you will, within a season, get the nutrients right back into the rhizosphere where the plants need them. And they'll all be in a form that never saw the surface. It went directly from the detritus through the soil directly to the roots. So it keeps away from surface contamination and all sorts of other things. And what accumulates in the bottom of the trench is this thin layering. And if you look at it really, really close, you'll see that it's actually made of sort of diamond-shaped, needle-shaped sort of things. And they're fractal. The smaller, if you break them up into smaller and smaller pieces, the pieces that it breaks into look like the pieces that they started out with. And that's because there's quasi-crystalline. It's not really crystalline, sort of short range order, kind of like clays. But once the carbon is in this form, you have to set it on fire. You have to take it to its ignition temperature was like 570 degrees Fahrenheit or something like that. You can plow it, you can crush it, you can blow it in the air, and it'll stay as black solid without decomposing. So the way this happens is that you have coal swamps where organic material of all different kinds falls into a well-drained, this is not a boggy swamp, this is more like the Everglades, you know, kind of a flowing river, rich in nutrients, but always moving. And what happens is as the organic material sinks down below the water, it's kept out of the atmosphere, and it can begin to decompose or transform without oxidation, really, from the atmosphere. And if the hydrogen that would normally accumulate under decomposition is constantly swept away, and the pH isn't allowed to drop, and it stays at a neutral pH away from air, then it will begin to form peat. And if it's able to remain out of the air and the water completely drain out of it, and the overburden is allowed to just squeeze all the water out, then all of the little fibers of peat begin to coalesce together, and that's the formation of coal. Not sure. Okay.
That's right. No.
So you can tell, and they look at this very carefully with coals when they mine and look at them for their energy content, moisture content, and kinds of organic material that's in them. And for each one of these organic material, is there something wrong?
It didn't advance.
It looked like it went to the website, to a website.
It's possible.
Try and advance a slide again.
It doesn't. Okay. I saw it actually coming up with a little box that I was trying to not pay attention to it.
Yeah.
Maybe it's one of the.
Okay, can you just hit?
Go reduce,
Oh, yeah, reduce. Yeah.
or
that would-
oops, I don't know how to use it. There we go.
Okay.
Yeah, I think you hit a live link is what happened maybe.
Oh, that's possible. Oh, yeah, that would be the yeah.
Okay.
Anyway, so if you think about it, this swamp system is actually a special kind of detritosphere. It's a very specific kind. And when you have these conditions, this magical or no, geological process occurs that preserves characteristics of the original biomass and forms a particular kind of masserole, as in with rocks are formed out of the clustering of minerals, and coals are made up of the clustering of masseroles. Pretty much the same thing. And depending on where it started out, whether or not it was humus from, say, for even the Great Plains or something like that, or trees or whatever it is, it will make different kinds. And so they generalize these different kinds and characteristics. Oh, it went to a site again.
Yeah.
Not.
Yeah, just minimize that.
Oh,
over
minimize it.
here. Yeah, and that'll get you back. There
Okay,
you go.
but
And then try not to click on there. It's live.
where is it? Okay, so I'll just go down like right here. Is that-
Yeah,
there we go.
There we go.
Okay, so each one of these different classes you can read here just real quickly. Plant cell walls with visible structure. They go through this process called gellification, and that's the process that actually transforms it from peat into a coal, because it becomes structureless at that point, the way the masseroles are. Anyway, you can see that all these different things, algae form one, peat matrices with other materials mixed in with them. They make all of these different kinds of masseroles. And so this is compost. This is the compost, gone to its logical conclusion. And so if you look at this, what you can see is these last fabrics, after all of the sugars and carbohydrates and lipids and all that stuff are used up in the process of transforming this material, and then it in turn becomes nutrients for everything down the line to the detritosphere and the porosphere and the rhizosphere and so forth. But the last materials that are left after all that are these fragments of the things that make wood strong and tough, and the stuff that makes cork strong but light, and things like that. And these are the fragments that are left over. And so if you look at these fragments and their chemical structure, this used to be part of a root or something like that, and now it's just this part of those cells that's left hanging around. And also floating around in the same soup are these things that have one cyclic compound on one end, and then a hydroxide on the other. And what that does is it gives it one end that likes organic bonds, and the other one that likes the mineral bonds. And so this links between the two. So when you talk about cation exchange complexes, this is what you're talking about. This is the basis of a cation exchange complex, the mineral side of it. Well, it turns out that with these things, under the right conditions, if there's no water, no soil, no air, and no disturbance, then these begin to coalesce with each other, and they end up turning into, this is a model of the very basic unit of a coal. It has all the bonds that a coal can have in it. So it's represented in that way. But you can see it's just made up of those fragments that comes together. And as long as you don't have minerals and too much water and that sort of thing getting in the way, these things will coalesce. And it turns out it's a biological process, not a geological process. And it happens really, really quick when you have the right conditions. And these fragments, as they begin to coalesce, this is sort of a two-dimensional view of it. This is in 3D, rotating it. And you can see they're very, very open structures. Well, this is exactly why if you pick up a piece of coal or something, it's so light. It's amazingly light. And this is why there's so much open space in it. These chains just bump into each other and click and twist and whirl and come together. And it turns out that they can only get so large. A mass roll can only get so large because it just, the ones out on the edge just can't hold together. But the more concentrated it gets on the inside, the more it can hold. But all of these bonds that are all concentrated in here, this is why coal has energy. All of these bonds clustered in around each other because they're high energy bonds. And so in order for this transformation to occur, you have to have it isolated out of the atmosphere so that these facultative anaerobes dominate in the biology. This is along the same lines, though a little different, as the Korean natural farming sorts of things. But here we're strictly looking at facultative anaerobes and not obligate anaerobes. So, so you have to be absolutely strict about not getting any mineral soils in these trenches, because they absolutely stop the processes that you're trying to promote there. Water gets in the way in a bunch of different ways. It allows obligate anaerobes to get in there, and they start reducing the iron in the soil, and things just, it's really, they can turn it into a real mess. So you want to keep it as far away from groundwater as possible. So these are just some articles that reinforce all of the different reasons why keeping soils out of the trench is really, really important. So this Fitton reaction is when iron reacts with organic matter, it can really tear it apart. And this is the way they did sewage treatment before chlorine was around. They would take this particular form of iron and mix it in with sewage sludge and stuff like that. And it would just like obliterate the organic, the sludgy material, and turn it into finer and finer stuff that could easily be filtered out. And because the sludge, you had no chance. And so that's when they figured out, this Fenton. There's an interesting story behind it, but it has to do with German chemistry, and therefore very sort of frightening. But anyway, it turns out that this thing happens all on its own. But if you have the wrong critter in there, they will emit this enzyme peroxidase, and it will increase the badness of this situation tenfold. So, and then these iron reducing bacteria that suddenly proliferate under these circumstances are if you inoculate the soil with them, they increase the emission of carbon dioxide by 140%, because this Fitton reaction now has this peroxidase going with it. But it turns out that if you're out in a field and just looking at what's going on out there because of these and other processes, that this really high number, that's 30% lower than what's happening out in the soil in the field. So just saying. Anyway, so all of this comes together to demonstrate that all you have to do is have the organic phase just a little bit out of whack, and you can absolutely tear up all of the organic material you're putting in it, particularly if you plow it. We would plow it with a metal plow, but if you're able to cycle nutrients without involving soil in the nutrient cycling process, then you don't have to worry about this at all. So back in the 50s, this other fellow thought about this idea of, wow, biomass like turns into coal. How does that happen? So I started taking samples of biomass of different kinds and plotting it out and looking at, on the vertical axis, up here is a lot of hydrogen relative to the amount of carbon. And down here is no hydrogen and all carbon. And on this axis is a lot of oxygen and no oxygen. So down here at the corner, it is all carbon. And so as you watch this transformation of first biomass, then into peat, then into lignite, then into coal, and then eventually into anthracite, but that takes sort of metamorphic processes. You see that it's this one continuous process. Well, along with the hydrogen and oxygen, all of the other nutrients that were in the biomass, they're leaving too. And so you have these conditions, which obviously can exist because this process happens in nature. And so being able to pull them together and kind of make them happen as fast as they can. Well, I'm sorry to say, I have to admit it, that's what a chemical engineer does. They look at chemical processes, they figure out enzymes and substrates and surfaces and shakers and stuff that optimize the conditions for the reaction to occur. The only difference is everything, every step of the way in here, it's all biology and sort of, it's all biology. It doesn't have anything to do with machinery or anything like that. You're using the actual underpinnings of nature. And so begin to be able to plot out all of the different parts of not only the parts of the biomass, but where these things were being deposited, for instance. And they found that we had these, because all lipids have this ratio of carbon to hydrogen and all proteins have this ratio and so on and so forth, you can plot them all out in these zones. And you can begin to look at, these are just chemical processes, the oxidation reduction we were talking about, the difference between having it out, being decomposed in the atmosphere where it can oxidize versus at the bottom of a swamp with lots of hydrogen where it can be reduced. So this is that line. Well, it turns out that sort of straight out from this plot, there's this imaginary line coming straight out from us where it doesn't move in any of these directions as it decomposes. And that is the actual line, that this decomposition line that Van Crevelen was pondering. And so we set up a system where all the components for allowing that to happen, we use wood chips and fungi up in here to seal it off from the atmosphere instead of water. That way you don't have to drain it. As a matter of fact, it just barely goes through the peat forming phase in here and it goes through that pretty quickly because there's no water. As a matter of fact, all the water is being drawn out by all the shoulder-to-shoulder worms in the walls of and their kindred spirits in the drillosphere. are all just literally drawing the nutrients and the moisture out of this system. So it can't, so it leaves, and it leaves behind what? The carbon, because none of these guys need it. They're interested in the other stuff. They just leave it behind. It accumulates here. And as long as no water comes in and decomposes into methane where it bubbles through. Well, another important part of this is that, you know, the word carbohydrates, see, that tells you that there's actually water in there someplace. Well, it turns out that under these conditions where it can't be oxidized or reduced, that the hydrogens and oxygens that you saw leaving in the Van Kervelen chart find each other and turn into water, brand new water molecules. They're called juvenile water. And under the right conditions, you will have brand new water coming out of the transformation of carbohydrates. So it's a remarkable process, but and you have to have just the right conditions for it to happen, but it will. So concentrating carbon, the drillosphere is absolutely critical in drawing out the hydrogen and oxygen and the nutrients out. And this also ensures that nutrients are efficiently recycled into the surrounding soils. And that those nutrients end up being utilized by this whole cascade of critters living in the pores and on the surfaces and on the roots and all that stuff, on the surfaces of the fungi, all over in this stuff. And what it does is it eventually coats all of the mineral surfaces in the soil with this goo that keeps its mineral characteristics. The reason you want to keep it out of the trench, it hides it underneath this organic patina. And that's the patina that holds together really good, well aggregated, high organic matter soils. And because they're very, very hydrophilic, they draw water in just exactly like a cellulose sponge. So this basically the cellulose sponge goes on the outside of all the soil minerals, and it keeps them from being from participating in the decomposition of carbon in their surroundings. So this is yet another Van Kervelen. You have oxygen on the bottom and hydrogen on the top. And so as you go from 0 hydrogen to up to 4 hydrogens, you see that molecule, well, that's methane. 4 hydrogens for every carbon. And this is the line that takes biomass and takes it up and turns it into hydrogen. And no surprise, it has to have a source of ever-increasing hydrogen floating around. That means a low pH in order to drive in that direction. Whereas if you have oxygen continuously being added to the soil by, say, plowing or something like that, then the biomass is constantly being pulled with more and more oxygen, eventually out to where you have a 2-to-1 ratio of carbon to oxygen, and that's CO2, and by it goes. And it can, in both cases, it's taking carbon with it. And so if, on the other hand, you follow that magic line in which no oxidation reduction or any of those other things happen, it follows this line that in this on this curve all the way down and eventually into coals. But along the way, if there's enough oxygen around, if it's not losing oxygen fast enough, moving in this direction fast enough, then it goes down and it turns into peat. And so what that means is it's not buried quite deep enough in order to keep from turning into peat. And so that's why peat bogs are all over the place and coal deposits aren't. Anyway, as it continues down, this is the zone where lignin, the stuff laying around in the soil after it's been decomposing, as it moves down toward becoming coal, this whole zone in here are all the different kind of lignins. And you can see that this is where a biological material is like already halfway to becoming coal. So on the way, this biomass is losing all the other things other than lignin and those other suberin and all those things that are preserved, and they're being gobbled up by bacteria and a bunch of other things, and some of the carbon goes with them. And that carbon, as long as there's not, as long as they're not respiring carbon dioxide, that carbon ends up being in their bodies and ends up just in the cycle of soil organic matter. So that's where all the soil organic matter cycles around and around and around and around, just like the edges of our trench. So as you continue down, eventually you get down into the zone down here is 5. This whole zone is lignite, and within the confines of that are torrefacted materials. That means they've been burned. So if you were looking for where, say, the char material that is left over from controlled combustion, this is where you would find it, in this zone right in here. Anyway, it continues on down and goes into hydrocarbons and eventually into real coals. But the zone that we're talking about is this zone right in here, where you go from lignin into lignite. And so what we do is we grow materials that have lots and lots of lignin and all these other things that we're interested in. And we see how successfully we can generate these layers of ever richer carbon materials on the bottom of these trenches, and coming up with better and better ways of preserving them, keeping the water out and all those things. So we grow lots and lots of sunflowers, was a particular crop that we looked at, and look very, very carefully at how effective and what the parameters and how to improve it and all those different things, all guided by real practical science. And no. And this operation, this part of the operation, was organized and carried out by Anna Eichner, my colleague in all of these matters for sure. And so I'll turn it over to her, and she can talk about this really amazing way that we were able to, the only way we could have ever carried out this research.
Hello. So where do I click?
On the screen, see your cursor? It's right
Okay.
there.
So in September of 2019, we had a workshop at the farm, and we grew a variety of sunflowers all summer. All of these were known for their height. Lily was the award-winning sunflower of Josephine County County Fair for like 4 years in a row. So we had to get some local seeds, and they proved to be, these were all like 10, 12 feet tall. So we harvested the sunflowers, and we measured and cut and arranged them by size, because when you put them in the trench, you want to put the biggest ones in the bottom, and then the medium, and then the smaller ones. Some of the sunflower heads got gigantic. Some of the bases of the sunflower stalk where we cut, they had a diameter, they had a circumference of 10 inches. Where's the thing here? So we collected the data. This form was made by a fellow land steward, and you can see the before and after. You know, we're citizen scientists, and this is a little messy, but it did all get put into Excel spreadsheets. And so while some people were working with the sunflowers, others were digging this trench. The trench is 2 feet deep. about 18 inches wide. And for this demonstration, it was about 20 feet long. So you can see that the soil from the trench was put up on the bed. Okay, so here's Scott starting the next section. So this was the first demo, and it works overall, it works better to do it in little batches because one tote pretty much fills up one linear foot, depending on how big they are. Or let me just say, one tote fills the base for one area. It could be 1 foot, it could be 2 feet, depending on the size of the stalks. So here we've got the biggest ones, then the smaller and smaller, and then the leaves. And some of the leaves were like 15, 20 inches across. And at the end, you put the sunflower heads face down, but the more packed they are, the better it is.
That's oxygen.
Less oxygen. And then we did not have wood chips, so we used the next best thing, which was leaves and little short branches to top it off, to once again hold in the oxygen. Also, we covered it.
Mhm.
Now, you know, when you go to AAA, they kind of joke about having to go to map class to learn how to fold the maps correctly. Well, this is a good example of our protocol for tarping or landscape fabric covering the trenches and beds not being in place.
Yeah, but the one in the background is nicely.
Right, so this one's neat. But also it was really hot and we wanted to cover as much of the trench and the soil as we could. Okay, you ready?
Yeah. So as far as having a, practical angle on this, and particularly an angle where you're promoting, responsible climate action in, land management, and actually doing something with the land that, offsets the CO2 emissions, and to just find out how much impact that could have. And then the other side of it is that there's an emerging carbon market, and the value of carbon, I went through a number of articles and I sort of looked at the span of what Europe, feels like it's worth as far as, the permanent removal of carbon out of the atmosphere. And if you can demonstrate that you can actually do that, then it's worth a certain amount in order to do that. And so the number that's usually talked about in the United States is $25 a ton, and it's just sort of assumed that 10% of that, or no, anyway, a certain percentage, depending on how aggregation works in your area, goes to a fund that basically handles the transactions and verifies that it's there, and pays the insurance to make sure it's there, so on and so forth. And so you end up with they get $10 a ton, and the farmer actually ends up with $15 a ton. In Europe, the numbers range from $40 to $80 a ton, and the European Conference said it was 57 euros a ton. So it's all over the place. So, like, does that actually make sense as far as if you wanted to use your land instead of for agriculture, for ecosystem services, and engage in this commodity instead of soybeans or something? And so I went through some, just to figure out what the ranges of the bottom line is. What is your net primary production on where you are in the world and with your precipitation and all that stuff? And this slide is probably meant more for agricultural economists, but if you go through and crunch all the numbers and do all the conversions and look at the averages and so forth, if you look at $40 for every metric ton, which is 1,000,000 grams, and it ranges from $40 per million gram to 80 per million grams, and you're able to meet the net primary production of an average agricultural field, average farmland, which has a range. It can go from, if you're in the richest soils in America, you can come up with $136,000 per hectare, but there's not a lot of that around. But it ranges down to $1,600 per hectare at that range in carbon trade. If you look at wheat production at $150 per metric ton, and you have a fairly average corn production of about 4.5 million grams or metric tons per hectare, you end up with 672. So you see that just with all the uncertainties here, that it actually is in the range of feasibility if you can pull it off, because you have to make sure that the carbon, there's no way you can make it back into the atmosphere, and there are 5 components. I was going to tattoo them to my arm, but I forgot. That permanence and anyway, that if you're going to engage in the carbon trade market, you have to demonstrate that you can verify it. Well, one of the tough things about doing soil carbon sequestration is you have to have hundreds of sampling sites all over a field in order to find out what the average carbon content of the soil is, and you have to do it over time. When you're doing it in these trenches, all of the carbon is in one place, and it's pretty much uniformly distributed in that place. So what you have to do is sample it in one place, and you have a very good idea of what it is in the square feet of your acreage that's accumulating that material. So it's much easier to verify and so forth when it's in this form. So over the last 10 years, this is a view just before we purchased it, or it was a purchase for putting in nourishing systems research and teaching and all the other things that we've tried to do there. And you can see one of the things we recycle are billboards. They make being able to manage the weeds on 3/4 of an acre with one 70-year-old person actually possible. And once you sort of have it down, it's sort of like, I don't know, rigging a schooner or something like that. It's a lot of fun. But anyway, so out in here you see these sunflowers that were grown for preceding year before COVID, I guess it was, right?
During
COVID, yeah. And they went through exactly the same process, took the same numbers. We were going to plant 2,000 plants this year, but it looked like water was an uncertainty, so we decided not to spend or designate that many seeds to an iffy proposition.
So we use the volunteer artichokes.
Yeah, so as it turns out, artichokes are taking over our property, and artichokes are without a doubt a more carbon-rich biomass than sunflowers. They're just astonishing. So we're very excited about the fact that they just sort of showed up and said, "Hey, take a look at us," And I went, "Wow!" And not only that, they spread like thistles. So over the course of that 10 years, we've put together place has been able to generate a lot of food, and underneath that tarp and underneath those peppers, that is a carbon sequestration cell. It is taking, and a nutrient cycling cell. It's regeneration, regenerative agriculture, kind of in one place. Cycling nutrients, it's accumulating carbon, it's harvesting an enormous amount of water out of biomass, storing that water in high organic content soils, and it builds a biodiversity where you have the detritosphere, the drillosphere, the porosphere, and the rhizosphere all protected, by very, very careful, little or no till. I mean, by till, I'm talking about a cultivator rake or a bow rake. Nothing pretty much, well, a broad fork in the early days, but after the soil becomes, gelled, then you wouldn't want to disturb it. And at that point, it's pretty much gets to where it's plant and harvest, particularly when you understand which one of the weeds are the good guys and which are the one you have to get rid of them as soon as they emerge. So our works in progress we're continuing. This is taken this morning. Here we're harvesting off these artichokes and artichoke stalks and continuing on. And with this new area that was opened up, it's like almost 3/4 of an acre. The number of artichokes or anything else that you wanted to grow out there is enough to get a very, very, very large data set on varieties and conditions and plantings and so forth. So we're really excited about that. And the end result, the whole reason we're doing it is to build these berms that will grow up out of the ground. They'll be about 3 feet high in the middle, 6 feet across. And that is where we'll plant our forest garden. And we want the increased surface area of a berm, so we have more surface area to generate the, at least 2 of the layers in the 7 to 9, depending on who you ask, layers of the forest garden. And so this is all generating the soil for that forest garden. And another thing is that I was able to rescue all of these ficus, fig boughs from the OSU burn pile and use them in putting in and learning, the intricacies, or actually the fun of building these wattled gabion. Now, these are not retaining walls. These are designed to be a habitat that the top bed will have thornless blackberries. We have how many? 45 individual plants, 16 varieties. And each one of them has a completely different kind of a cane. There are creepers and arching ones. And so in this picture, you can see the board that's laying at the base of the broad fork. Those are the beginning canes that I'm beginning to, in the second year canes, they just like out of nowhere die. And so you trim them off. And that's what I'll be continuing year after year after year after year, keeping the wattle in place as the material I'm putting in now turns into soil. And so you just, every fall, you harvest off all of those canes and stick them in between the burlap that you replace periodically and the wattle wall. And this wattle wall is aimed just south of winter solstice sunrise. And so it has this beautiful aspect all winter long. And these materials, catch that low angle sun and keep it into the soil. At the same time, all this stuff is essentially composting. So there's that warmth. And then it's sheltered out of the wind. So all these things together should make for a really, really beautiful gabion hillside. And the strawberry plants you see down in front, there are gazillions of them now. All of those will be transplanted up, and the lower gabion will be those raspberries, and then there will be strawberries. We fill with strawberries, and then there's a garden down below where we'll have I don't know, lingonberries or something growing down there. But it's in that little lower sloping hillside, we'll have keyhole stepways that'll allow you to, very thoroughly harvests off the blackberries and strawberries from down below. And there's a archway up above that has the same variety of blackberry planted on it either side that you can walk through and harvest from above. So this is, kind of our attempt at citizen science and good land steward experiences and building community and so forth. And I'd be happy to entertain any questions. This PDF of this slide pack will be available to anybody who wants it. So.
We'll talk about the resources.
Each one of the references that you saw in here, the pictures and all of that stuff, they're all thoroughly referenced. Whatever. They're all thoroughly referenced in the back of it.
Okay, hi Scott from the other room.
Well,
That
can you hear me?
was, can you hear me? Scott, can you hear me? Just want to make sure
Let's see. Stop.
you can just stop your share. Yeah, there you go. Okay, all right.
Okay.
Great. Okay. Well, that was really dense.
I can't hear. Let me see.
Can't hear me. Shoot. Yeah. Hang on.
She's trying something on her end.
Okay, now can you hear me? Okay, now can you hear me?
Rachel, we can hear you. I think the problem is on Scott's end.
Okay, shoot. Okay, well, I'm going to go in the other room with my questions. We're just going to keep on with this technical difficulties. Okay.
She's coming to your rescue.
Okay.
So I don't have
He
audio.
muted himself.
Well,
Okay.
no, I'm
Can't hear
muting
anything.
doesn't.
Yeah, that's all right. For some reason.
We're having conversation.
Yeah, that's all right. That's okay. So I'm just gonna kind of sit here with you, I think, and
Sit there.
I
ask
like this
questions. No.
two level thing. This is
Yeah.
really nice. It's like makes my arthritis go away. I like it.
Okay, good. All right, well, that was really a whirlwind chemistry tour. That was, I was scrambling and Googling, and if I would have been dropping definitions into the, pull forward a little so folks can still
Oh.
see you there.
Oh, okay.
We
Into
can
the-
be
into the
having,
zone.
exactly, we can be like Joe Rogan. I would have been Googling and dropping definitions into the chat, but I was definitely Googling things and reiterating. You were saying everything and it was dense. It was unfamiliar terms for me, but I mean, one of the things I wanted to clarify, and folks, feel free to, if you can go back and think of any questions, there weren't any in the chat, but we will look for them.
Mhm.
Yeah, definitely ask questions. So I was just going to kind of reiterate, and I know you've been talking about this
Mhm.
for a while, that
Mhm.
this process of putting the stuff in the trenches,
Mhm.
that you're kind of, so it sounded like you're not going all the way to creating coal. You're
No,
stopping in
well,
the
no, you are-
midway.
No, you see, there's, it goes from compost then into peat.
Uh-huh.
And then once peat begins to condense, those fragments that are left over from the lignite and stuff like that, they actually start to form coal.
Which is
They
lignite,
form,
basically.
exactly. They form a
Lignite.
specific
Lignite.
lignite.
Yep.
Which is and in this case, it's a specific mass roll called humanite. And when you do essentially sort of composting, that's the mass roll you'll end up with.
And the mass rolls are the little microscopic kind of pieces left over from the plant material that's
Uh-huh.
being decomposed
That-
or that's
that-
being converted,
right.
really, metamorphosed.
Yeah, and the thing about it is, if you think in geology, you have a melt, and all these crystals begin to form out of the melt as it begins to cool, and they
Uh-huh.
build these crystal complexes
Right.
and stuff. It's the same kind of a process, except it's silica, which is valence of +-4, and carbon, which is +or-4.
Okay,
Both
okay,
of them can polymerize.
okay,
That's magic.
okay,
Gives rise to life and computers.
okay. Okay, so one of the things I wanted to clarify in terms of your process there, you were weighing all of that
Mhm.
material that you were putting
Mhm.
into the trenches. And so then were you weighing it afterwards, or
No,
how
no, no,
were
no,
you
it
actually?
goes away.
It just goes away. So in
And then
that
at the
matter,
bottom of the trench, you take a probe and you go and you look and see what kind of condensate,
Mhm,
because it actually is an organic condensate. That is forming on the bottom of the trench and in layers. And it's beautiful because the interaction between the reason we have to have that mat of what I call the hugelkultur zone at the bottom is it can't touch soil. Soil eats it.
because of the iron.
Well, and a
reactions
bunch
that you
of
were talking about.
manganese has one. You count them all. They just
Okay.
they're all.
So with the carbon market and the regenerative
Mhm.
agriculture, what are they counting on? Just not tilling? Or what are they counting on in terms of the carbon sequestration?
You mean the current thinking?
Yeah, like what are
Well,
they paying for?
I have to tell you that it really similar to the biofuels market, it's essentially a scam. You cannot, and I've shared with you this article that goes through all the literature that demonstrates this. It's in the general press. You cannot sequester carbon in soil. You can cycle carbon in soil. And in order to cycle lots of carbon in soil, you have to keep it very, very, very healthy. And if it, for any reason whatsoever, is unhealthy, okay, so if you're going to get paid carbon credits for this very, very healthy soil, and you have to guarantee it's going to be healthy for 100 years, how does that work? See what I'm saying? It's not really sequestered. It looks like it's sequestered. It's there now, but all you have to do is change your management practice or have a drought or whatever. Well, that's why they have a huge, when part of the carbon trading is you pay into an insurance pool that says that if for some reason, the natural disaster, all of your carbon goes away, you can draw from this pool in order to cover yourself, because no
I see.
rational lawyer or land manager would sign into something where you're promising something for 100 years.
Okay,
See what I'm saying?
okay, yeah, I'm
Well,
not
see, that's
too
the
familiar with
well, the thing
with the
about when
process
you
in terms of the agriculture.
generate this material, you can plow it, you can
Oh, because
dig it
it's
up.
in that lignite. It's not
will
gonna
stay-
volatilize
it
into
won't.
the atmosphere
You
unless you
have to
burn it in
set
your
it on
car.
fire.
Yeah, okay,
Well,
got
the
it.
other thing about it is this accumulates, if you do it right, quite a bit of this. Well, when you go and down buy a jug of Humax or any of those, that's what you're buying. Exactly what's in the bottom of that trench.
Hmm.
Well, if you dig up the material that you're accumulating and you put it in a bag and nobody sets it on fire, everybody's fine. It becomes a soil nutrient someplace else. It wasn't combusted. It's out of the atmosphere. Everything's fine. That's the advantage of this form. That, and you're doing it all in one location. And you can sample 1 or 2 locations and see the variance in it. And demonstrate
So
this.
what would that be? So let's see here. Okay, John Oliver has
Mhm.
been talking about carbon offsets. So somebody put a link in there.
Mhm.
So how could you, I mean, in a practical, I know how much work you guys put into
Mhm.
this, but in a practical kind of sense, what would a person, I mean, how could farmers do this?
It's not farming in the sense of you have this as a part of your food production. As a matter of fact, this process should be done on wastelands.
Uh-huh.
It should not compete with land values for arable land because we need that for food. This is ecosystem services. It's a different business model.
Mhm.
It has different risks, all, it's still a commodity, just like soybeans. It's just that nothing leaves the farm.
Mhm.
Well, that's a big thing. You don't have to have roads to carry the materials. You don't have to have trucks to build. All you do is it just disappears in the ground, and all you have to do is prove it.
Okay, so back to your trenches. Let's see here. Wait, Megan is now answering a question from our Soil and Water Conservation District. She says, is this material actually lignite or a pre-lignite form of recalcitrant carbon, which I asked earlier, but then I
Mhm.
figured out what that was. A cursory search indicates that lignite is formed on a scale of around 60 million years.
Yeah,
Right?
not true.
Yes, yes.
The reason, well, okay, that is true. It's the reason is that in order for the lignite to form, it has to accumulate in a swamp. That swamp has to be drained without making it into the atmosphere and not ripped open by some geological or other process. You see, in order for it to happen in nature, it happens very, very slow. But just like any other chemical engineer, you go through it and figure out how the process, what are the critical elements of the process, and how to accumulate all of the relationship between and all you have to do is understand how old growth forest floor nutrient cycling systems work. And we know a lot about that, largely because of Mr. Stemmis, but that's all you're doing is you're optimizing. You're having the detritosphere right next to the drillosphere, right next to the porosphere, to be able to move those out. And they leave behind the carbon, and they leave it behind in a way that the atmosphere and hydrogen ions can't get at it. It's exactly the same process. It's just that since it's so optimized, and there's no limitation. The trench can keep up with you. We have to look all the time and grow as much extra stuff just to, it's like feed me Seymour, you know what I'm saying? It's like,
Right, right.
and the thing is, if they fall down, then that drillosphere zone dries out, the worms die, all of this worm cheese that they have generated, all this really just wonderful soil dries out, dies. It's heartbreaking,
Mhm.
you know?
You have to
It's-
keep feeding it.
Exactly. This is crazy, isn't it? And I'm warning you people, don't get into this unless you're.
So what if,
Works for the goat.
so if a person is just using a kind of more conventional composting
Mhm.
pile method,
Right.
then what's happening with the carbon?
It's all going in the atmosphere.
Okay, that's,
Oxidation.
uh-huh,
I mean, you're stirring the compost, so it does oxidize.
right.
So all the nitrogen and all the carbon go out of it, and you're left with these shreds of lignite and all those other things. The same stuff that you would, that would
Oh,
sort of, make it to the bottom of the trench. It's just that all of the nutrients got, well, not all of the nutrients, all the volatile nutrients got volatilized, and many of the enzymes and stuff like that got pretty well cooked on the way.
okay, can you kind of clarify for Alex, sorry, not clear why we want to produce coal rather than compost?
Because it won't go back in the atmosphere. This is
The
not,
idea is this is carbon
Right.
sequestration, putting
Right.
it into something.
but see, here's
that's
the
not
other
gonna
deal.
fall
At the
apart.
same time, you very, very efficiently cycle the nutrients in your biomass, so you don't need any amendments. And as a matter of fact, they cycle so fast. I mean, if you have a compost pile, you take the biomass, you take it someplace, you turn it, all the nitrogen and carbon, or bunch of the carbon leaves. You have this pile of stuff that you have to then carry back and then distribute it around. Well, with this method, the nutrients that came out of that part of the bed go in next to that part of the bed. So see
Yeah,
what I'm saying?
yeah.
You don't
It's
have
a
to worry
lot
about
of work
nutrients.
though, Scott.
No, it's not.
No.
I'm telling you, compared to,
So last year we
Turning.
grew 15 different kinds of melons, watermelons, cantaloupes, muskmelon, Asian melons. And we would have sampling. So when all the buckets got filled, we would weigh them and then we'd
Yeah.
put them in a specific trench. So there was so much biomass for this 15-foot area. Within a month, it was 1,500 pounds of biomass that went in, and on either side of the trench, there was like a 6-inch zone of basically compost tea
Right,
that had just
It was wet. The
percolated.
soil was wet with
From the
compost
trench.
tea.
right.
So you don't need a
right.
brewer.
Right,
See what I'm saying?
yep,
The brewer is right there.
right.
It has evolved over some, period of time to, this is the way nature works. All you're doing is farming with nature and the way that nature works. That's.
So are you guys going to be publishing this, kind of the results of the weighing and the scales? Is this research gonna be kind of quantified in some way?
Well, no, it's quite quantified
Mhm.
as far as that's concerned. But peer review, no doubt about it. It could go in acres. It's gonna go in New Pioneer
Uh-huh.
because we write, we're regular writers for them.
Right,
So all of this stuff, as a matter of fact, the two articles that are coming are composting and then the deep dive in trench composting. But the very first article that we published, that was published in there, it was about us. We didn't write it. Well, actually, no, never mind. But and it was about the Climate Victory Garden, which is the backyard scale of this very thing of trench composting.
okay,
You go out and find a 9x14, I can't remember what, anyway, area of land, and then you do a lasagna, and we go through this step by step, and
Mhm.
anyone can do it, absolutely anyone. And after 2 years, you're beginning to develop this trench. Well, just by doing it, you'll learn so many things because you have to observe, do this when this happens. And so you're engaged with all these step-by-step processes that are going on. Well, they have all these underlying meanings that you'll discover on what you see them. But through the course of it, you learn how to do regenerative agriculture.
Right.
Observe it.
And isn't, I mean,
But
part of,
the
I
other
think
part of
the
it is-
idea is that
yeah.
the terra preta, the
Yeah.
Brazilian soil is one of the thinkings is that it's this material that you guys are creating.
There's a
right?
huge controversy because there's people who believe it's black carbon
Mhm.
and
That was burned and put in there, created.
Right. And so if you look at, the pyrolysis and where it falls on the Van Crevelen plot, it overlays lignite and those. So it's depending on how carefully you look at the material, what test you use on it. Now, see, the reason,
Could
one of
you
the reasons-
carbon date it?
well, yeah, you can, but that won't necessarily tell you what molecule it is, or if it's a mass roll or a molecule or whatever.
Oh, right, of course, that wouldn't necessarily, right. But I guess. Yeah,
Now, see, one of the things about, and I'm pretty excited about this, we finally got 3 samples that the way you can tell you have this mass roll, this humanite, is there are some industry standard tests. It's called vitrinite reflectance. You shine blue light on it, and then with a photometer or whatever it is, you measure the amount of reflectance in it. And every single mass roll has a range. That's one of the ways you tell what mass roll it is, by looking at its vitrinite reflectance. So all you have to do is shine a light at it. But in order to verify which mass roll it is. But if you've ever looked at a piece of fairly fresh coal or petroleum, you notice there's this iridescent shine to all of them: coals, lignites, petroleum, kerogens. And that's one of the ways you spot organic molecules in a water stream, is you're looking if it has an iridescent swirl on it, there's some kind of carbon-based compound in it. Well, the mass rolls have exactly the same thing. And what it is the all of those fragments have matted together so tightly that they finally begin to reflect light at certain frequencies. And that has to do with their, their molecules. And, just like the reason that light goes through a crystal is a certain color. It's
Mhm.
because the distances between the crystal lattices. And this is the distances between these mass rolls.
Okay, all right, well, we're getting close to our ending time. Let's see, somebody says, I have a lot of elderberry canes every year. Would that work along with artichokes and sunflowers?
Yes, because they have a pithy center.
Okay,
Anything that has a pithy center, think about the surface area on the, or even an open center. Because what you're looking at is the maximum amount of surface area in the biomass.
okay. And then, just as a final, I don't know
Mhm.
if you can summarize for the
Mhm.
at-home, say gardener, small scale gardener,
Mhm.
what is the take home? What
Well,
3 steps should they take to participate in this, to be
well,
part of sequestering carbon?
if you want to really simplify, if you're interested in growing nutrient dense food that you are sure is nutrient dense, this is a very, very easy way. Once you get these, it's a little work up front, but once you have it installed, that's the nature of indigenous technologies. There's all this stuff up front, but then you just do it for 500 years. You know, right? You just harvest and plant. No, that's the way it works. That's why that's the pay anyway. And that's the way this is. It takes some work up front. And, you know, but once you have it in place, every single time the plants go through this cycle, all those critters that are on the aggregates and living there, and they're drilling into the aggregates, every single cycle, they pull more nutrients out of that pool and put them in. So the system doesn't just cycle nutrients, the same nutrients. It gets richer and richer and richer.
On these lateral sides, and you're covering it, you're
Mhm.
keeping it covered, so it's
Yeah.
not getting into the air. The
Well,
organisms are just
what you're
bringing those
doing-
nutrients in for the roots of your
right.
of your
The
crop
critical
plant.
thing is you are creating, as far as anybody that's below the wood chips and the tarp is concerned, they are in an old growth forest soil. That's the ecology you're creating. And these old growth forests are where these peats and coals normally accumulate. They used to be all over the planet. They were gone 8,000 years ago. I mean, you know,
Right,
in order to find the coal.
right. Okay. Well, I think we will call it a night, and I will send a link to the recording so that you guys can review this.
Yeah.
And thank you, Scott, for your time, and I'm gonna ponder it all
Been a
for the
pleasure,
future
been a pleasure.
myself. Okay. All right, take care, everyone.